Hello everyone. In the last video, I calculated the electric field everywhere of a charged sphere, both inside and outside the sphere. Now, the charge density or the charge distribution was uniform, and it was a pretty complicated problem. But in this example, we have the same sphere, but in this case, the charge distribution is not uniform. So the question is, how do you calculate the electric field of an object with a non-uniform charge distribution? Now, this is a very good exam question, so I require your complete attention. Now, I'm going to walk you through the steps so that you will understand exactly what to do if you see such a problem in a test. Remember, we are using Gauss law, and Gauss law essentially states that the electric flux, the total electric flux through a closed surface, is equal to the charge enclosed by that surface divided by epsilon naught. This is the statement of Gauss law. Now we are going to use this simple statement to calculate the electric field inside and outside this charged sphere. Remember, we will follow the following steps. 1, we have to determine the symmetry of the problem. In this case, it is spherical symmetry. 2, we need to draw our Gaussian surface in the appropriate region. So in this particular example, we will draw our Gaussian surface inside the sphere as well as outside the sphere. So you need to take that into consideration. But first of all, we know that the volume charge density rho is defined as dq divided by dv. That means that dq is equal to rho dv. This is 1. 2. The volume of a sphere is equal to 4/3 pi radius cubed. This means that dv is gonna be equal to 4/3 pi bracket 3r squared dr. 3 takes care of 3, so this implies that dq will be equal to rho, which is alpha divided by r, multiplied by dv, which is going to be 4 pi r squared dr. So one of these r's takes care of that, so we will be left with 4 alpha pi r dr. Hence, this means that the charge at a distance r will be equal to the integral from 0 to r, 4 alpha pi r dr, which is just gonna be equal to 2 alpha pi r squared. This gives us the charge at a radius r from the center of the sphere. Now, we are going to keep this because we'll use this. So keep in mind that q sub r is equal to 2 alpha pi r squared. We will use this pretty much soon. So take note of this problem. So the next step is for us to choose our Gaussian surface. So let's begin with case 1, where r is less than capital R. In this case, we will choose our Gaussian surface in here, this is R. So from Gauss law, we know that the total flux through any closed surface is equal to Q enclosed divided by epsilon naught. So this means that E multiplied by A is equal to Q enclosed divided by epsilon naught. So what is the area of a sphere? So we have E bracket 4 pi r squared. The enclosed charge we calculated, this is 2 alpha pi r squared divided by epsilon naught. You can clearly see that this takes care of this and this. So we are left with E equal to alpha divided by 2 epsilon naught, where r is less than or equal to big R. So this is the electric field inside the charge sphere. Unlike the other example we did the other day, in this particular case, the electric field inside the sphere is constant. Why? Because alpha is a constant, epsilon naught is a constant. This is just a number. This implies that the electric field inside the charge sphere is a constant. Now, the next case is we will analyze the situation in which R is greater than big R. So case 2, R is greater than big R. So here we will choose our Gaussian surface to look like that. So this will be our R. We know that EA is equal to Q enclosed divided by epsilon naught. Now Q enclosed is the total charge. This is Q sub big R, which is just gonna be 2 alpha pi big R squared. So this means that E 4 pi R squared will be equal to 2 alpha pi big R squared divided by epsilon naught. So if we simplify, this will give us E to be equal to, see, pi takes care of pi, 2 here takes care of 2 there. So this goes down, you will have here alpha divided by 2 epsilon multiplied by R squared divided by small r squared. This gives us the electric field outside of the charge sphere. So if you noticed, the electric field from the center of the charge sphere, this is the radius r, it's constant and then decreases. So here the field is constant, but here E is inversely proportional to R squared. Please, if you have any questions with regards to this example, I will appreciate it if you ask questions below, so that I will be able to help you understand these very important concepts. Thank you, and remain blessed.